All right, in this lesson, we are going to talk about modular arithmetic. So let's introduce modular arithmetic, talking about time. And you can make very big charts to help describe this, but I'm not going to be quite that detailed. But I want to start thinking about hours after noon on a day. Okay, so let's just pick a day. So let's say we're at May 15th at noon is where our example is starting. Okay, well, if I said what is 5 hours after noon? Well, 5 hours after noon on May 15th is 5 p.m. That's a real easy one to figure out, right? However, if I said something like 14 hours after noon on May 15th, you would figure out that, well, wait a second. Once I start calculating that, at some point I don't have a 13 in my time. Instead, it cycles back and begins at 1 again. So once I hit 12, it begins at 1. So from noon till midnight is 12 hours, so we do 2 hours later, and we find out that 2 hours after midnight is 2 a.m. So 14 hours after noon is 2 a.m. If I did 24 hours after noon, we would find out that it is exactly the same time as it started. It is noon. It is 12 a.m. It becomes 12 a.m. So we all should have a pretty good understanding about how clocks work. So let's think a second and think about, well, when am I going to have 5 o'clocks? Well, 5 o'clock is going to happen every 12 hours. So if I want to find out when is it going to be how many hours after noon is it going to be 5 o'clock? Well, the first one is 5 hours. The next one you should be able to tell yourself is 17 hours, right? 17 hours after noon would give you 5 a.m. And then after that would be 29 hours. 29 hours after noon would give you 5 p.m. And you could keep going, and if you notice, all you're doing is you're adding 12 each time. Okay, so every time I want to get to the same time, just 12 hours later, I just add 12 hours. And so what we call this a cyclical system, where you're cycling back through. If I want to find out other times that it's 2 a.m., I just keep adding 12 hours. 26 hours later, it's 2 p.m., 38 hours later, it is 2 a.m., and so on and so forth. So we can go through and we have a good idea about being able to determine how many hours after a certain point give you the same times. And it's all done in this system where 12 creates your cycle. So another way to think about this is columns and numbers. That was done on a system of 12. Well, we could do a system of like 7, let's say. And we could start with 0. That was our noon. And then go 1, 2, 3, 4, 5, 6. If you notice, there are 7 numbers there. Then if we just keep going, and we keep counting up by 7s, we notice that we start creating columns of numbers. And these columns of numbers act the same way as the cyclical time system, right? If I said, what column is 48 in? Well, what you'd have to look for is, you could keep writing these down, or notice that in each one of the columns are just separated by 7s. And if you notice, each one of these, if I divide each of those by 7, I get remainder 6. 13 divided by 7 is 1 remainder 6. 20 divided by 7 is 2 remainder 6. If I divide 48 by 7, I get 6 remainder 6. And so it ends up in this remainder 6 column. And so 48 eventually down here would have been in that 7th column. Every multiple of 7 is in this first row. Okay, it's got remainder 0, so it's in the 0 column. Anything remainder 3 would be in the 3rd column, so on and so forth. So we can do problems involving columns of numbers. Those are all, again, the same ideal cyclical. Okay, we give some definition to this, some formality to it by using the word modulus. And what we say is m, and then we put in parentheses modulus, but we don't write modulus, we write mod. M mod n basically means m is less than or equal to n minus 1, and it's greater than 0. These are always, we're dealing with integers, and we're dealing with positive integers as we do this. Later on, we can discuss negatives and things like, we'll discuss negatives and whatnot. But in general, when we talk about modulus, we're writing something mod n. And what this is saying is m is the remainder when the number is divided by n, right? So if we go back to what we just did, and we look here, 48, well, our m is 7 because there's 7 columns. So we do 48 divided by 7, and we get 6. So we could write 48 as 6 mod 7, because 6 is the remainder when 48 is divided by 7. Okay, so when we talk about modular congruence means two numbers that can be written the same using modulus. So for instance, if we go back again to our columns are a good way to understand this. Every column experience modular congruence. 6, 13, 20, 27, 34, 41, 48, all of those can be written as 6 mod 7, because every one of those has a remainder 6 when divided by 7. All of these are written as 3 mod 7. So those numbers all have modular congruence. So we find out that there's an infinite number of modular congruences for each number. All right, so let's look at some problems. One example says write 213 as, the 3 line means modular congruence, x mod 7. Well, you do what we did before, which is divide by 7. When we divide by 7, we end up with 30, remainder 3. So that means 213 is equivalent to 3 mod 7. So all you do is you're just looking for remainders. This problem, what is the 413th number in the following list? Well, first off, if you notice, this one's going to be a little bit confusing. It would be a better let's do it like this, and let's put the 0 in there, because our 0 is going to be our first number. No, we don't have to put the 0 in. We're fine with putting it like this. So if we do our, think about this. If we end up with modular, whatever this is, we're doing modular 6 because the pattern has 6 repeating numbers in it. So we divide 413 by 6, and we get, we do our division. So we get remainder 5, and so 413 could be written as 5 modular mod 6. So the 413th number then is 5. Okay, because if you would have had every multiple of 6 would be a 0, every remainder 1 would be a 1, remainder 2 would be a 2, and so on and so forth. So since it's remainder 5, and 413 is 5 mod 6, that means that the 413th number in this list, as it keeps repeating itself, is a 5. Find a 4-digit number that is congruent to 5 mod 6. Well, if you go back and think about what this problem was like back here, we're just looking for a number that has remainder 5 when divided by 6. Well, I can think of a really easy number that is evenly divisible by 6, and that would be 6,000. So if we add 5 to that, 6,005 divided by 6 would give you 1,000, remainder 5. So 6,005 would be congruent to 5 mod 6. So all you do is you find a multiple of your modular number, and then you add whatever the remainder is. And so that leads us to this other definition, which we call a residue. And a residue is a way of saying this remainder. Okay, so whenever we're talking about residues, we're always saying the remainder in modular arithmetic. Or another way to say it is if we have m mod n, m is the residue. And by the way, m will always be greater than or equal to 0, and less than n. And always be an integer. So if it says find the modular 5 residue of the following, that means basically find the remainder when divided by 5. So 42 divided by 5 is 8 remainder 2, so the residue is 2. So it's just the remainder. 274 divided by 5, well, that's going to give you a remainder 4. So the residue is 4. Or you could write these as 2 mod 5, but our residue is actually just that remainder part. So it's just another definition of problems to do. Okay, that gives us an introduction to what we do, how we talk about modular arithmetic. We'll be doing some more problems and examples of how you can use that to solve other problems.